In this chapter, we're going to be looking at rotational motion. And so we're going to look at how many times a tire turns per second or a record player. So we're going to look at this simulation of a ladybug versus an ant on a record player. So we're going to put the ladybug kind of towards the center and the ant on the outside. So they're lined up in a straight line. So if we start this simulation, as they travel around the circle, the ladybug is moving linearly a lot slower than the ant. And you can see that here. They've got the speed of the ladybug and the speed of the ant. But if we were looking at how many times or how many turns does the record make, let's say per minute, well, the ladybug and the ant are completing the same amount of turns per time period. So their rotational velocity is going to be the same. And here you're given 26 degrees per second. We could speed this up a little bit. And so it's a little bit more obvious how fast the ant is going linearly compared to the ladybug. But they're making the same amount of laps per time period. Another example of this would be if you've ever been in a marching band. So, when you're in a marching band and you come to a corner, you have to turn that corner. The people on the inside of the corner have to slow down while the people on the outside have to move faster for everyone to stay in a straight line. When we're working on this chapter, all of your problems need to be done in radians. So on your calculator, you do have a mode where you can switch between degrees and radians, and you'll want your calculator to be in radian mode. If you're in trig especially, you'll have to watch out for this because sometimes trig might be in radians or degrees. So you may need to switch back and forth depending on what class you're in. So the first symbol that we have is arc length. And so if we're looking at a circle and we want to look at arc length, so we have the center of the circle. Arc length just means how far are you traveling around the circle. So what is that length there? And that symbol is S. We also have radius, which is going to be the distance from the center to the outside. And the angle in radians we can find by S divided by R. So if we have an arc length, let's say here is the length that we want to measure. Here is the radius. The degree we would find by S over R. You will need to know how to convert between radians and degrees or revolutions and radians. Now, again, if you've been in trig, this might be something that's familiar. So 1 radian is equal to 360 degrees over 2 pi, or you could say 180 over pi. 1 revolution is equal to 2 pi radians. And you will need to convert between all three of these different values. So if we look here, express the angular velocity of 45 revolutions per minute of a record in radians per second. So we'll start out with the 45 revolutions per minute. And so if we have revolutions per minute, revolutions will be on the top, minutes will be on the bottom. Revolutions on top, so we're going to put them on bottom, and we're converting to radians. So if we look back, our last slide told us that between radians and revolutions, 1 revolution is equal to 2 pi radians. That's a 1. So we will use that as our conversion. We also wanted this in seconds. So minutes is on bottom. We need minutes on top now. to get our seconds on bottom. So there's 60 seconds in 1 minute. And then we would take 45 times 2 pi divided by 60. I know in math what they want you to keep things in terms of pi. I personally would rather you go ahead and type in and get a decimal for our answers. When we are looking at average angular velocity, the symbol for that will be omega, which looks kind of like a funky W, and it's going to be in radians per second. Instead of um, meters per second, this angular velocity will be radians per second. And you're going to solve for that with your angle over your time. Instantaneous angular velocity is just the velocity at one specific point in time. If we're looking at different points on a rotational body, they're going to have different translational speeds, but the same rotational speed. This is exactly what we were talking about with the ant versus the ladybug. So if we have a point, let's say that is here, and another point that's out here, this point is going to move translationally, or you can think linearly, slower than this point out here. But if I said, again, how many rotations per second are they making or per minute, they would be making the same amount of rotations or have the same rotational speed. Now we're looking at angular acceleration. So angular acceleration, the symbol kind of looks like a fish. It's an alpha. So it's going to be your change in your angular velocity over time. Just like regular linear acceleration was change in velocity over time, now we are angular velocity over time. So instantaneous angular acceleration is going to be radians per second square for the units. Every point on an object is going to have the same angular velocity and the same angular acceleration. Now, when we're connecting linear motion to rotational motion, we're going to be using a lot of the same equations that we've used before, but just in terms of rotational motion. So, to kind of show you how the symbols compare, so our omega is the same as v, alpha is the same as a for acceleration, your degree is the same as your distance, and then the time again is the same. You may want to write these down. If you're a person that can think, oh, I know this v is the same as omega, that's fine. These are all of our old equations, but now replaced with the new rotational symbols. So write these down on your equation sheet, use them however you're going to need to, but you will need these for our problems. So if we look at this first problem, a bicycle wheel rotates with a constant angular acceleration. So angular acceleration is this symbol. If the initial velocity of the wheel is 2 radians per second, so rotational velocity is the W or the omega, time is t of 0, through what angle, so they're asking basically for a distance, does the wheel rotate in 2 seconds? Part B, what is the angular velocity? So basically the final velocity. So we have, and you can see here where I've worked this out, we have angular acceleration, we've got initial rotational velocity, we've got time, and we're looking for the angle. So we're going to use this equation here. And then it's just a matter of plugging things in like we did before. So we had initial rotational velocity is 2 times 2 plus 1/2 acceleration 3.5, and then t squared. So that gives us an angle of 11 radians. What's the angular velocity? Basically, we're doing vf squared equals vi squared plus at, but in terms of rotation. So we're using this equation and plugging it in and solving for uh, angular velocity of 9 radians per second. Tangential velocity is the linear velocity that's going to be tangent to your circular path. So when you think about a circle, if an object is moving around the circle, but then it were to shoot off at one point, this is the velocity that would be tangent to the circle. So that's what we're looking at, this tangential velocity. So v sub t is tangential velocity, and it's going to be radius times your rotational velocity. Tangential acceleration is going to be a sub t times radius equals radius times rotational acceleration. Now, this is going to be a multiple part problem here. So we're going to kind of walk through and see what we've got. And then on the next page, I'm going to show you how to work this out. So first of all, we've got a turntable rotating initially at a rate of 33 revolutions per minute. That's going to be a rotational velocity, and it said initially. Takes 20 seconds to come, and then it comes to rest. So a final velocity. What's the angular acceleration? So there's our fish symbol, assuming this acceleration is uniform. So if we go and look at the next page, the first problem I see, revolutions per minute, we need that in radians per second. So here you can see, let me erase some of this. This is what we knew. We're given in the problem that 33 revolutions per minute has to be changed to radians per second. Then we can use this equation here, just like vf squared equals vi squared plus at. Now we're using that in terms of rotation. Plug in what we have, and we get an angular acceleration of negative 0.17 radians per second squared. So it's slowing down. Part B, we can go back. Part B says how many rotations does the turntable make? So it wants to know how many turns it's making or what angle before coming to rest. So the rotations, here we're looking for angle. So we have initial velocity, final velocity, and we have t, and we're looking for our angle. So we can use basically like distance equals 1/2 vi plus vf times t. Now we're doing it in terms of rotation. Because it says how many turns does it make, basically how many times does it rotate. So once we get that angle, we're going to convert the radians back to revolutions to tell how many turns that it made. The next question is asking us what is the tangential velocity, and it gives us a radius of 0.14 meters. So we have our initial rotational velocity, and so we're using this equation and plugging those in. And then the last question asks, what's the tangential acceleration? Again, we're using the radius and then the rotational acceleration and multiplying those together.